Thank you, Gilles. Welcome everyone to this first parallel session. The first presenter is different than was mentioned in the program because one presentation was cancelled, but we found Hans de Waal. He was able to present earlier in the day. He's from the State Supervision of Mines, and he is going to tell us something about Dutch Wadden. I'll give the floor to you, Hans.
Thank you, Saskia. Okay, so I hope it's a pleasant surprise for you to find this presentation rather than the one you might have come for. Okay, so let me start by pointing out to my... oh, this isn't working, I think. Oh, yeah. We'll manage. Yeah, we'll manage. Yeah, okay. So my co-author, Matthijs Schouten, who's here in the room as well, colleague from State Supervision of Mines. But in fact, the work presented in this presentation is the result of the effort of tens of people, to be honest. And a lot of the results we'll just fly over it during this presentation, but if you want to know more about it, please have a look at the paper, and in particular in the references that are in the paper, because it's been a large piece of work. It's been executed from initial ideas in 2010 to finishing an application of the results in 2015 to 2017, so quite a period. Okay, let's start. What is it about? It's about this area. This picture here, which shows you the wetlands in the north of the Netherlands. I have another picture on that here. What you see here is this area here, which is wetlands behind barrier islands. As it says there, it's a coastal wetland system. In fact, I can look at the slide here as well. There's tidal flats and barrier islands. It's a very important migration birds feeding ground, so it's an environmentally very sensitive area. It's also a UNESCO World Heritage Site. It's a very dynamic landscape with water flowing in and out and sand flats moving around. Of course, it's affected by sea level rise. To some extent, you've always had natural subsidence here, otherwise this area wouldn't even exist. So there's sediment loading and subsidence, and the combination of both creates these tidal flats and barrier islands. But it's also a natural gas province. These green things that you see, if this will work, yeah, that you see here are all gas fields, and they're actually being produced. So it takes an extensive legal, technical, organizational framework that's in place to prevent damage. But concerns have always been there, but they became larger around 2010, when it became clear that the subsidence that was taking place here was strongly non-linear, and so delayed. Initially, nothing much happens, and then after a production for 5 or 10 years, or a pressure drop of a few hundred bars even, all of a sudden it accelerates. Okay, this is how it works. I mentioned it before. You have these sea sediment loads coming in and out of the wetland area, depositing sand and silt in the area. But of course, if you, in this area here, cause subsidence, natural subsidence, and on top of that, sea level rise and gas production induced subsidence, that can become a problem. So the gas field that has the longest history is the Ameland field, which has been producing for more than 50 years, and it's been carefully monitored over those years. The green dots are benchmarks on the land surface, and the squares are permanent GPS stations, and the circles are temporary GPS stations that are put up every year for measuring campaigns. Okay. So how does it work? Well, it's mainly the rate that is important. As I said, you have this play of sediment being deposited and the land sinking, and as long as the sediment deposition can keep up with the rate, the average rate at which the land sinks, it's okay, the area will be stable. But it cannot be above. And there's something called the natural subsidence limit, which is based on an analysis of what's happened in the last sort of 1,000 years. And a very safe number for that is about 6 millimeters per year, average over the area can sustain and not get damaged. It's probably higher. It's probably around 10 millimeters per year, or maybe even higher. But it's so a very safe level for that has been taken. Now you have the predicted sea level rise, eating that away over time, and then there's a gap in between. You see the gap here, which is actually available for subsidence due to human activities, gas production in this case. So there's existing fields. You see them here in orange, and you could do more things. And you can actually fill it up to the 6 millimeter per year upper limit. The problem, though, is it's very difficult to predict. It turns out to be very difficult to predict the subsidence and the subsidence rate. You see that in this plot, where you see various prognoses and actual measurements, and turns out it is really difficult. The parameters in the models that are being used are uncertain. The subsidence, as I mentioned before, is nonlinear, strongly nonlinear, with production and pressure drop. There's uncertainties in the influence model. How does it translate the compaction in the reservoir to the subsidence at the surface? There's aquifers that play a role. There's a sand layer, or a salt layer on top that is creeping. And it's very difficult to measure accurately the deep subsidence. Okay. So you see that illustrated here as well. You have the gas here underneath these aquifers, and how far is their pressure communication, influx of water. And of course, if there's influx of water, there'll be larger areas that get affected by pressure drop. Here you see laboratory measurements that have been made, a large range. There's a salt layer on top. This is what you get when you have different assumptions on the viscosity of the salt. Quite marked differences. Here's different compaction models. And you have this, which observations showed initially nothing much happens, and then all of a sudden the compressibility of the reservoir seems to increase by a factor of 3 or more. Yeah. So given all that, the regulatory response has been that gas production can only take place if you can actually demonstrate that under all conditions and all scenarios you remain in control and the substance will stay within the allowed limits. And to do so, and in particular after this strong nonlinear substance was observed, a very extensive development program has been put in place with advanced monitoring data analysis tools, and also to see what is causing this nonlinearity. Starting around 2010, as I mentioned. The approach taken, studies were started up. We involved an NGO, the Wadden Vereniging. The regulator was very much involved, and the 2 large study programs were executed, LTS 1 and 2. LTS 1 was really looking at all those various possible mechanisms, 6 or 7, that could explain this nonlinear behavior, and developing tools, and LTS 2 was applying them to this case that's available where we have 50 years of data in the Ameland field. Now, there's no time here, of course, to go through all those results in detail. If you're interested, I think it's a great piece of work that has been done. Have a look at the paper, and in particular at all the background documents. So we'll just fly over it here. There was a very authoritative external steering committee. Professor Bout was in there, Professor Zimmermann was in there, some of those names you might know, internationally recognized world experts in rock mechanics. Same for subsidence measurements, we had experts. There was an independent review that looked at the study at the end. This is Professor Teatini, who's here in the room at the moment. And all the results have been published in open literature, including peer-reviewed papers. Okay. So, the basic approach is simple. You have pressure scenarios, geomechanical data, that creates all kinds of predictions over a large range of possible scenarios. Then you have the data, you confront the 2, and you try to find the scenario that best matches the data, and then you improve on your uncertainties. It's illustrated here. It's called the ESIP workflow. Initially, you have very little observations and an uncertainty, and as time progresses, the yellow lines are all the various scenarios. As time progresses, the measurements actually allow you to constrain the number of surviving scenarios over time and reach more reliable predictions. But next to this, you have to prove that while you still have large uncertainties, under all of the surviving scenarios, you'll be in control and you'll even be able to stop. It's called the hand on the tap approach. Okay, so as I mentioned, the LTS work was mainly looking at all the various possibilities that could explain the nonlinear behavior and then developing the tools to be able to test them against real field data for the AMALAT. Okay, some examples. I showed you the monitoring network. What's used in the work is double differences rather than compaction relative to or subsidence relative to a stable reference point. You have lots of scenarios because the aquifers can actually have quite an influence on the pressure distribution in the aquifers, the permeability there, the presence of gas, etc., etc. And we used an advanced ensemble-based data simulation methodology to compare the results of the various predictions against the real field data. Okay, LTS2 was then taking all of those tools and applying them against the AMALAT data. Okay, the filter particle approach is used. We had 58 depletion pressure scenarios. You have very little control of what happens in the aquifer because there's no wells there. And we had some 20,000 subsidence members, so in total, well over 1 million scenarios. And then the data. In the analysis, proper care was also taken to estimate the uncertainties, both in the models and in the data. Here's some examples. So here's those 58 pressure scenarios in the aquifers. Here's pressure development in various places in the aquifer, depending on which model you choose for permeability or residual gas in the aquifer. And here you see the parameters for the salt, where the typical tau, so the response time of the salt is between a month and 70 years or so. The rate type compaction model, also with its uncertainties, etc., etc. Here you see the range of uncertainty in the compressibility data, quite large. Here you see what I mentioned before, typical response times in the salt from a month to 70 years. All of that was used to generate all those various scenarios. The workflow in detail, no time to go through that, but have a look at the paper if you want to know more. Here you see the results. So this is applying all that science, all that methodology to the AMALAT dataset, the 50-year dataset. What you see here is what happens after the confrontation of the predictions with the data in three times, 93, 2001, 2017. You see, initially in 1993, that's after 5 years of production, there's still quite a number of scenarios possible. That's the green bars there. And it takes up till 2001 when you see that the a number of the, why is this not coming? No, yeah. A number of these scenarios are disappearing. That's scenarios in particular with a strong drive from the aquifers. And then nothing much changes from 2001 to 2017. And pressure scenarios, bars that are close to each other, are also in reality close to each other. So you really start to focus. Okay, this is the result then. On the right, you see the outcome. So here's that 6 millimeter per year maximum that's allowed. Here is the base case scenario with the 95% uncertainty, and that's all based on the surviving scenarios from confronting the data with the various, the 1 million predictions. Okay. Conclusions, it works. A scenario-based approach taking measurement and model uncertainties into account is really key. Statistical analysis, data simulation really help. Without prior knowledge, the initial uncertainties are very large, factor 2 to 3, so we shouldn't be surprised that we saw those changes. Yeah, saw those changes initially, where things were just jumping ahead, up and down into the predictions. You need extensive, accurate long-term data to have discriminative power, at least 10 years or so, before you really start to narrow down on the possible scenarios. Luckily, what we saw here, that the parameters in the geomechanical model actually correspond to those derived from the laboratory experiments in the long run. That gives a lot of trust, of course. The effect of lateral aquifers seems very limited. It's not just the salt that explains it. There is truly nonlinear compaction behavior in the reservoir rock itself. And all the extrapolations of the surviving scenarios within the 95% confidence band result in a situation where control is maintained. And Also, you have to show that when you see that happening, you say, hey, we're going wrong, let's stop, then the brake will work. Now, of course, the effect of the brake diminishes somewhat towards the end of the field, because when you're at the end of production, there's only limited braking that you can still do. Okay. That's basically it. So, questions? Yeah, otherwise this won't work.
Okay. Yeah.
Yeah, it works.
Thank you, Hans. Are there questions in the audience? Yes.
Where does your 6 millimeters a year of allowable subsidence come from?
Right. That's based on geomorphological studies that were done for the Wadden Sea area, where people from, I think it was Deltares, largely looked at the history of the Wadden Sea over the last 1,000 years or so, and the sort of sea level rises that occurred, and so they, based on that, made an estimate. I think the mean outcome of that was something like 10 millimeters a year, but then a safety margin was put on top of that as well. So that gives the 6 millimeters. There's some debate on that. Yeah.
Thank you. More questions all the way in the back?
So thank you for your speech. I have a question about, you talk about the strategy. So how can we know it's good or not? How can we validate it? It's not the model, but it is the strategy. So how can we know it's good and suitable for any region or any local area?
You mean the validity of the methodology?
Yeah.
Or
Your strategy, because we need to propose.
category? Oh, strategy. The strategy. Yeah. No, I think it's a very general strategy. I think this strategy would work under quite enough. It needs to be adapted, of course, to local conditions. But in general, in particular, all the various tools that have been developed can be applied elsewhere.
Oh, yeah. I mean, how can we know it's workable or suitable for any region? In your opinion?
Yeah. You have to believe in science. It's basically the message.
Yeah, that's the reason I'm so curious about it. Thank you.
Right. Yeah.
We have time for another question. Yeah.
Hello, thank you very much for your presentation. I have a question. Has actually this workflow somehow mandatory for the companies who produce gas? Has become mandatory?
Right. The way this worked, when in 2010 the discussion started on, hey, do we have a problem here? It was decided as part of the license, granting the license, that the operator had to demonstrate to the approval of the regulator that he was in control. And so the final say of whether or not these results were appropriate and allowed a controlled situation was with the regulator. Yeah.
Okay. Thank you.
It's time for one more question. There is, yes.
Thank you for this presentation. I only a very fast question. You mentioned that the lateral land subsidence is about 6 millimeter per year, right? And I didn't take that subsidence rate by a gas production here.
How much is it? You
Yeah,
mean?
yeah.
It depends on, because there's a number of fields here, but it's 3 millimeters per year, sort of, in that order of magnitude. But the more gas fields are being taken in production, so we have to go back. I don't think, yeah, this slide here. So here you get an ID. So here's the 6 millimeter limit. Here you see Ameland is the green wedge. So that is about, well, slightly less than 2 millimeter per year at maximum, and now less because the field is almost finished in production. And so there's this room left for other fields and new fields potentially. Yeah. And there's discussions on that going on in the Netherlands. Of course, things change over time. The sea level rise scenarios get adapted, and et cetera, et cetera.
Okay, thank you, Hans, for your interesting presentation. Give him a round of applause, please. And time for the next speaker.